Hello friends, welcome to my lecture on properties of Z transforms. The topic of properties of Z transforms will be covered in two lectures. This is first lecture on the properties of Z transforms. In the last lecture we had obtained the values of Z operating on un equal to n and Z operating on un equal to n square. So now we will talk about Z operating on cos n theta. Okay. So let us suppose we have to find Z of cos n theta. We know that cos n theta can be written as e to the power I n theta plus e to the power minus I n theta by 2. Now by applying the linearity property of Z, we can write it as 1 by 2 Z of e raised to the power I n theta plus Z of e to the power minus I n theta. Now let us recall the result. We can write, now let us find Z of e raised to the power I n theta. E to the power I n theta we may write as Z of e to the power I theta raised to the power n. Here we shall apply the formula for Z transform of a to the power n. We know that Z transform of a to the power n is Z over Z minus a, provided mod of Z is greater than mod of a. So let us take a equal to e to the power I theta here. So then we shall have Z over Z minus e to the power I theta, where mod of Z is greater than mod of e I theta, and mod of e I theta is what? E I theta is cos theta plus I sin theta. So mod of e I theta is square root cos square theta plus sin square theta, and you know that it is equal to 1. So this is Z over Z minus e I theta, provided mod of Z is greater than 1. Okay. Similarly, Z transform of e to the power minus I n theta we can write as Z transform of e to the power minus I theta raised to the power n. Now here we shall take a equal to e to the power minus I theta, and then again apply the formula Z transform of a to the power n equal to Z over Z minus a. Now where mod of Z is greater than mod of e to the power minus I theta, mod of e to the power minus I theta is also equal to 1. So this is equal to Z over Z minus e raised to the power minus I theta, where mod of Z is greater than mod of e raised to the power minus I theta, which is also equal to 1. And let us now put the values of Z transforms of e to the power I n theta and e to the power minus I n theta. So then we shall have, so hence Z transform of cos n theta will be equal to 1 by 2 Z over Z minus e I theta plus Z over Z minus e to the power minus I theta, and we can write this equal to this is Z minus e I theta into Z minus e raised to the power minus I theta. So this is Z square. Okay. So and then so it is 2Z square minus Z times e to the power I theta plus e to the power minus I theta. Okay. So we can write it as 1 by 2 2Z square minus 2Z cos theta divided by Z square minus e to the power I theta plus e to the power minus I theta, and then plus e to the power I theta into e to the power minus I theta is e to the power 0, so we have 1. So this is equal to z into z minus cos theta divided by z square minus 2z cos theta plus 1. So z transform of cos and theta is z into z minus cos theta divided by z square minus 2z cos theta plus 1. Similarly, we can find z transform of sin n theta. So when we write z transform of sin n theta, we shall have similarly z transform of sin n theta. This will be equal to 1 by 2 I. Okay, let me write it like this. First we can write it as z transform of e to the power I n theta minus e to the power minus I n theta divided by 2I, and by using the linearity property, this is 1 over 2I z transform of e to the power I n theta minus z transform of e to the power minus I n theta, which is 1 by 2I. Z transform of e to the power I n theta is z over z minus e I theta, and this is z over z minus e to the power minus I theta. This is equal to 1 by 2I z minus e I theta into z minus e raised to the power minus I theta, and then z square times z square minus z e to the power minus I theta minus z square will cancel, and we will get minus z times e raised to the power okay, let me write it like this. So this is equal to z minus z e to the power minus I theta, and here we will have plus z e to the power I theta. So z times e to the power I theta minus e to the power minus I theta, and e to the power I theta minus e to the power minus I theta is 2I sin theta. So we shall have 1 by 2I sin theta into z divided by z square minus z times e to the power I theta plus e to the power minus I theta plus 1. So this is 2I cancel, and we get z sin theta divided by z square minus 2z cos theta plus 1, where mod of z is greater than 1. So that is how we find the z transform of sin n theta, and then z transform of a to the power n cos theta we can obtain by damping rule. Let us recall the damping rule. We know that by damping rule, if z transform of a sequence un is uz, then z transform of a to the power n un is equal to uz by a. So z transform of a to the power n cos theta. So z transform of a to the power n cos theta will be equal to in the z transform of cos n theta. In the z transform of cos n theta, which is z into z minus cos theta divided by z square minus 2z cos theta plus 1, let us replace z by a. So we get, and this will give you z into z minus a cos theta divided by z square minus 2az cos theta plus a square. So we get z transform of a to the power n cos theta by using the damping rule, and similarly by using the damping rule we can obtain the z transform of a to the power n sin n theta in the z transform of sin n theta, which is z sin theta over z square minus 2z cos theta plus 1. We replace z by a to arrive at az sin theta over z square minus 2az cos theta plus a square. Now let us discuss the shifting properties. Like we have the shifting theorems in the Laplace transform, here also we have the shifting theorems. Now the first theorem is giving us a result when there is a shifting of the sequence un to the right. Suppose z transform of a sequence un is given by uz, then z transform of un minus k is equal to z to the power minus k uz, where k is a positive integer. Let us see how we prove it. We know that z transform of un, z transform of un is sigma n is equal to 0 to infinity un z to the power minus n. Okay. So apply this definition to the sequence un minus k. So z transform of un minus k is equal to sigma n equal to 0 to infinity un minus k z to the power minus n. Now z to the power minus n we can write as z to the power minus n minus k into z to the power minus k. This z to the power minus k is independent of n, so we can write it outside the summation. So z to the power minus k sigma n equal to 0 to infinity un minus k z to the power minus n minus k. Now let us define the index j equal to n minus k. So when index j is n minus k, since n begins with 0, n is equal to, when n is equal to 0, j is equal to minus k. So we have the summation of over j starting with minus k, and when n is infinity, j is equal to infinity. So we have infinity here. So what we get is z transform of un minus k is equal to n z to the power minus k sigma j equal to minus k to infinity uj z to the power minus k. Now k is a positive integer, so uj wherever j is negative, then we know that when we define the z transform, there we have assumed the sequence un to be equal to 0 when n is less than 0. So we will make use of that property of the sequence un. So z to the power minus k and uj, you can see here uj is 0 because whenever j is 0, uj is 0. So j which was starting with minus k here, okay. So all these values of uj where j is negative will be equal to 0, and so the summation will start with j equal to 0 and go up to infinity. So we have z to the power minus k sigma j equal to 0 to infinity uj z to the power minus j. Now sigma j equal to 0 to infinity u to the power uj z to the power minus j is uz. So what we get is z to the power minus k uz. So when there is a shifting by k on the right side, the z transform of the sequence un minus k is given by z to the power minus k into z transform of un. Now suppose there is shifting of un to the left. So if z transform of un is uz, then we shall see that z transform of un plus k, the sequence un plus k where k is again a positive integer, is equal to z to the power k into uz, which is z transform of un minus u naught minus u1 by z minus u2 by z square minus uk minus 1 over z to the power k minus 1. So this can also be said that here in the inside the bracket we have the z transform of un sequence, and from that we subtract the terms of the series sigma un z to the power minus n from n equal to 0 to n equal to k minus 1. These are the terms of the series sigma un z to the power minus n where n runs over 0 and goes up to k minus 1. Okay, so let us see the proof of this. Again recall the definition of z transform of un. Z transform of un is sigma n equal to 0 to infinity un z to the power minus n. So z transform of un plus k, z transform of un plus k will be sigma n equal to 0 to infinity un plus k z to the power minus n. Again we apply use the same procedure here, apply the same procedure. z to the power minus n can be written as z to the power minus n plus k into z to the power k, and z to the power k can be taken outside the summation because it is independent of n. So, z to the power k sigma n equal to 0 to infinity u n plus k z to the power minus n plus k. Now, let us define the index j as equal to n plus k. So, here n was beginning with 0 and ending at infinity. So, n is equal to 0. So, j equal to k. So, summation over j will begin from k and go up to infinity, because when n is infinity, j is infinity. So, z to the power k sigma j equal to 0 to k, sigma j equal to k to infinity u j z to the power minus j. Now, so what we have is z u n plus k equal to z to the power k, and then we have summation over j from k to infinity, and we have u j z to the power minus j. What we will do is now this summation can be expressed as sigma j equal to 0 to infinity u j z to the power minus j, and from that we subtract the terms sigma where sigma runs from 0 to k minus 1. So, j equal to 0 to k minus 1 u j z to the power minus k. So, we subtract this sum and add this sum. So, when we add this sum to the existing sum, that is sigma j equal to 0 k, sigma j equal to k to infinity u j z to the power minus j, then we will have this sigma j equal to 0 to infinity u j z to the power minus j. Now, this is nothing but u z, z transform of the sequence u n. So, z to the power k u z, this is u z, and minus you can write the terms of this sum. So, this is k, j equal to 0 means u naught, j equal to 1 means u 1 by z, and j equal to 2 means u 2 by z square, and so on, minus u k minus 1 over z to the power k minus 1. So, this is shifting of the sequence u n to the left. Now, in particular, suppose we want to get the value of z of u n plus 1. So, take k equal to 1 in this expression. So, z of u n plus 1 will be z times u z minus u naught, and when you take k equal to 2, z of u n plus 2 will be equal to z square u z minus u naught minus u 1 by z. And in a similar manner, when we take k equal to 3, we get z of u n plus 3 equal to z cube u z minus u naught minus u 1 by z minus u 2 by z square. Let us take, for example, the sequence u n to be equal to 1 by n factorial. So, let us say when u n is 1 by n factorial, z transform of u n is equal to sigma n equal to 0 to infinity u n z to the power minus n, and so z transform of 1 by n factorial equal to sigma n is equal to 0 to infinity 1 by n factorial z to the power minus n, and we know that this is nothing but the Maclaurin series expansion of the function e to the power 1 by z. So, we get the z transform of the sequence u n equal to e to the power 1 by z, and hence z transform of 1 over n plus 1 factorial. We know the z transform of u n, so z transform of u n plus 1 we have seen this is equal to z times u z minus u naught, okay, and u z is z transform of u n. So, if u n is 1 by n factorial, when u n is 1 by n factorial, we get z transform of 1 over n plus 1 factorial equal to z times z transform of 1 by n factorial minus u naught. U naught is what? U naught is the term occurring for n equal to 0 in the summation u n z to the power minus n and running from 0 to infinity. See, we have z transform of u n. Z transform of u n is sigma n equal to 0 to infinity u n z to the power minus n. So, u naught is the term in this sum which is there is the power of z is 0. Okay. So here z transform of 1 by n factorial we have seen, it is equal to e to the power 1 by z, and this is equal to 1 plus 1 by z plus 1 by z square into 2 factorial and so on. So the first term here is 1. So u naught is equal to 1. Okay. So this is minus 1 and this is z times e to the power 1 by z we have found minus 1. So z transform of 1 over n plus 1 factorial is z times e to the power 1 by z minus 1, and similarly z transform of 1 over n plus 2 factorial. So if un is 1 by n factorial, un plus 2 is 1 over n plus 2 factorial. So this is z square times uz is z transform of un. So 1 by n factorial minus u naught we have seen, u naught is equal to 1 minus u1 is the coefficient of 1 by z, which is also 1 here. So 1 by z, because z transform of un plus 2 is z square times z transform of un minus u naught minus u1 by z. So this is z square times e to the power 1 by z minus 1 minus 1 by z. So this is how we find the z transform of 1 over n plus 2 factorial. Okay. Now let us see an example where we shall find the z transform of a sequence un consisting of the terms 2 and 5 sin n pi by 4 and minus 3a4. So let us find the z transform of un. Un is 2n plus 5 sin n pi by 4 and then minus 3a to the power 4. A is given to be a constant. Okay. So z transform of un is equal to z transform of 2n plus 5 sin n pi by 4 minus 3a4. Now let us apply the linearity property. So by the linearity property, this is 2 times z transform of n plus 5 times z transform of sin n pi by 4 and then minus 3a4 z transform of 1. Okay. Now let us recall that z transform of n is z over z minus 1 whole square. We have earlier found the z transform of n, it came out to be z over z minus 1 whole square. Let us also recall the z transform of sin n theta. It came out to be z sin theta divided by z square minus 2z cos theta plus 1, and then let us recall the z transform of 1. So let us recall that z transform of a to the power n is equal to z over z minus a, provided mod of z is greater than mod of a. So here let us take a equal to 1. So taking a equal to 1, we get 1 to the power n, that is 1. So z transform of 1 is equal to z over z minus 1, provided mod of z is greater than 1. Okay. So now let us apply, let us put these values here. So 2 times z over z minus 1 whole square and then 5 times z sin theta is pi by 4 here divided by z square minus 2z cos pi by 4 plus 1 and then minus 3a4 z over z minus 1. Now let us recall that sin pi by 4 and cos pi by 4 both are equal and equal to 1 by root 2. So we will have 2z divided by z minus 1 whole square, and then we will have 5 times z into 1 by root 2, and then we shall have, this is 1 by root 2, root 2 2 over root 2 will be root 2. So z square minus z square root 2 plus 1 and minus 3a4 z over z minus 1. So this is how we find the z transform of the sequence un by using the linearity property and the standard formulae for z transform of n, z transform of sin n theta, z transform of a to the power n. So as I said, we have to remember the z transform of some special sequences here, which we shall need to find the z transform of other sequences, and these will also help when we solve the difference equations. So in the next lecture we shall discuss some more properties of the z transforms, like initial value theorem, final value theorem, and one more theorem is there which is multiplication by n. So we will discuss some more properties in our next lecture on properties of z transforms. With that I would like to conclude my lecture. Thank you very much for your attention.